My bad. It wasn't cut off. It was my viewing of screen with
Okay,
the
yeah, I kind of wondered about that. It's no worries. All right, well, guys, hello and welcome. I hope that you can all see me and hear me out there. It's great to see you again. This was not the way I intended it to be. I really appreciate that you've been reading your emails. That's why you're here and not in McCarthy Hall 480. So that's a good sign. Hopefully, the rest of everybody else in the class will make it in shortly. But I'm going to go ahead and get started since it is 1 o'clock. And I hope that you all had a good spring break. I hope that you were able to rest a little bit. I tried not to bother you too much, give you a chance to catch up on your rest after the break and everything. But yeah, I was not anticipating coming back to my parents' house again. It turns out that I think I told you my parents turning 80 this year. So they have a few physical challenges and some mobility issues. And it turned out that, well, just the way the timing was that they need me to be here this week to help them with some things. And so I really appreciate your flexibility. Maybe I'm saving you a little gas money today. Who knows? If I can make this a positive somehow. But you probably remember this. This is how we started the semester. And this time we're only doing this for 1 week. So I will be over here just this week. I changed my reservation to fly home. I'll be flying back there on Saturday. So by next Tuesday, we'll be right back into the classroom again, and should be that way for the rest of the semester. So that's the only real change. I did manage to get a copy of my notes. I didn't bring anything back here. I was not anticipating that I wouldn't be in California by today, but I do have my notes with me, which is the good news. What I don't have, of course, are the exams to pass back to you that you took before the break. Just a reminder about that. I posted a copy of the solutions to our midterm into the resources folder, midterm 2 resources folder. I posted the scores. You probably already saw some feedback on the take home questions that you did because I tried to make comments in Canvas for the take home part of the midterm. But in terms of the physical exams, the in-class exams, those are sitting in my office right now. And so they're probably a whole lot closer to you guys than they are to me. But we'll get those back to you next week on Tuesday. I really apologize for the delay on that, but hopefully you've had a chance to look at the solutions if you wanted to. And once you get the exams back, you'll be able to again go back and review that one more time. But yeah, the exams actually for most people, I think the second exam was actually even slightly better than the first one. Of course, there's exceptions. There's a little bit of up and down on the whole thing, but certainly, I think on the first exam there was only one person above 90%, but on this second midterm there were 4 people above 90%, which was really great to see. I don't know if my exams are getting easier or if the material's getting easier, or maybe you guys are just figuring me out over time and kind of have a better idea what to expect. I'm not sure, but in any case, that was really good to see. We have one more midterm to go before we get to the end of the semester and the final exam. I think our next midterm is on May 1st. So that should be easy to remember. The first day of May, which is a Thursday, I believe, we have our third exam, which is, of course, going to cover from where we left off in chapter 4 up through chapter 5 and even a good chunk of chapter 6. So we have only 2 more chapters to cover. Chapter 5 is about, as you can see, is going to be about differentiation. And then chapter 6 will be about integration. And that's really what we're going to spend the last third of our semester focused on, chapters 5 and 6, as kind of where we go from here. Don't forget, there is a homework assignment that's due tonight. I had 3 of you, I believe, come by my office hours last night to chat about it. That was great. Seems like it was going pretty well. As far as the rest of you go, if you have questions on the homework, I am going to have my office hours today in Zoom. So this evening, after my last class, I get done at 8 o'clock. I'm planning to hang around most of the evening. all the way until midnight, although by midnight I'll be half asleep because I am 2 hours east of you. So if you want to get coherent feedback from me, you might come in on the early side tonight. Just a suggestion, but I am going to try to keep my laptop on all evening long in case you do have any questions on that. But I'll be glad to help you out. So that's due tonight. The next assignment will be due next Tuesday. As I said, I'll be back over the weekend, so I'll be able to have some in-person office hours before we have to worry about that next assignment. The next assignment is going to be covering a little bit more on uniform continuity, actually, along with the beginning material here on differentiation. So kind of a mixture of the stuff from the end of chapter 4 with the beginning of chapter 5. Okay, well, I've kind of tried to get us reoriented a little bit. I know it's always hard after spring break to kind of get into the rhythm again of kind of the semester. I did open my chat box here. If anybody's got questions for me, and by the way, I appreciate all of the webcams on. Many of you have them on already, and that really helps me out with being able to see how you guys are following things. But you're also welcome to use the chat if you want to ask a question, or feel free to unmute yourself at any point here. We're going to do this just the same way we did at the start of the semester. I'm just going to use these 2 whiteboards here to kind of present the material. It's a little bit skimpy on space, and it's a little hard to erase this thing is really the big problem for me. But hopefully this will go through without too much loss of information. If you miss anything or you need me to repeat something or there's an issue, just holler out either with your microphone or in the chat, and I'll do my best to give a response. Does that sound okay? Is everybody with me on this?
Yeah.
Okay, sounds good. Great. Well, I'm glad that you guys are here, and what we're going to do today is start something completely new. By the way, I also forgot to mention, I assume you all found that video that I wanted you to watch. It had a proof of theorem 4.7 in it, which was really intended to give you one of the powerful applications of uniform continuity, which is that you can extend a uniformly continuous function from an open interval to a closed one. And the purpose of doing that is so that you can apply all of those theorems that we learned the week before spring break. Things like the extreme value theorem and the location of roots and the fixed point theorem, things like that. Those all relied on a closed interval. So that extra credit video, or not really extra credit, it's really supposed to be part of this assignment, to have you watch and submit notes on that video, is supposed to show you the proof of that result, which is really quite nice. So, okay, so with that set as the background, my plan for today was to start fresh. Brand new chapter, brand new topic, and we're going to talk about derivatives here. And this is really going to continue right where we left off in chapter 4. Chapter 4 was about continuous functions. And one of the first things that we're going to learn today, guys, is that if you're going to take a derivative of a function, it has to be a function that is continuous. Okay, you can't have a differentiable function that's not continuous. So this is going to be reinforcing and building off of the idea of continuous functions. So we're going to continue, or I should say extend, our discussion. So this is going to extend, this extends our study of continuous functions. So like I said, in a few minutes, I'll try to explain to you that a function can't have a derivative if it's not continuous. So we may as well think of this as a continuation of our study of continuous functions. Now, we all know that the derivative intuitively measures the slope of a graph. So if you want to have a visual understanding of the derivative, you probably, first thing that might come into your mind might be that the derivative measures the slope of a function, right? And it could be at any point in the domain of that function. And of course, you've all learned in calculus that this derivative, right, this slope idea has massive applications. Right? It allows us to solve optimization problems, which could be incredibly important in the real world. Maybe I should write a couple of these down. So the applications are many. I'm not going to make a complete list here, but I should at least just write down a few of the applications of these. So one of them would be optimization. Certainly in the real world, we are always interested in trying to optimize a function. A business might try to maximize its profits or minimize its expenses, something along those lines. We have things like related rates. That was one of the main applications of derivatives just in your standard calculus class, was solving related rates problems. Also, another one would be things like a Taylor series. We're going to talk about this actually in chapter 5, Taylor series approximations. So if you don't remember what that was, the idea is that you can take a function and sort of approximate it using a polynomial. Polynomials are really nice. As we know, they are continuous and they're pretty easy to study. We can try to find roots of them pretty easily and so on. So being able to do Taylor series approximations, that relies on the notion of a derivative. So these are applications of derivatives. Okay, that's what I'm giving you here. Of course, another one that's huge would be differential equations. Obviously, a differential equation has the derivative of the unknown function right in it, right? It's right in that equation. So solving differential equations, I don't think I need to explain why that would be important. We spend, engineers spend their lives learning how to solve differential equations that are, related to various types of engineering problems. So these are just a very short list. I'm going to put ... here because we could go on. We could talk about other things as well, but this just gives us a little bit of an idea. However, I do need to pause now and say that all of this stuff about applications is not really the focus of this class. As you know, Math 350 is a much more theoretical course. We are much more interested in sort of the underpinnings of this, the theoretical or abstract development of it. So you're not going to see me talking too much about the applications because you see those in your other calculus courses or in your specialized course in whatever field it is, statistics or physics or chemistry or whatever, right? Those applications will come out there. What we're going to do here, of course, is get under the hood of how derivatives really work from a theoretical, conceptual point of view. That's what Math 350 is about. So I'm going to be putting some of these applications kind of under the rug here. So we focus on the theoretical side. We are going to focus on the theoretical side of derivatives. We're going to try to prove those theorems, right? We're going to try to understand it from a very conceptual point of view. Okay. Again, I do have my chat box open, so if there's any questions, guys, feel free to throw those in there as we go along. The book has introduced a notation, and I'm going to, before I get into any definitions here and sort of start this new section, I want to get the notation down. We often are going to be working with intervals of the real number line. So we're going to let I, so capital I, which is going to be a subset of R, this is going to denote an interval. So in the definitions that I'm about to present, you're going to see the capital I showing up, and it will denote an interval. So this could be, it could be a closed interval like AB. It could be an open interval AB. It could be half open on one side or the other, right? So you could have anything like that. And then you can have intervals involving infinity as well. So we could have an interval from A to infinity, or from minus infinity to A, or we could have an open on the A side, and they could be open from either the left or the right. So there's tons of stuff like that that could be the interval that we're talking about. Okay. So far, so good? Well, let's just get into what is the definition of a derivative. You guys have probably seen this before, but I'm going to put this over here. This is definition 5.1 in the book. And again, let me know if you're having any trouble reading what's on my boards here. Just let me know. I can move my screen closer, or I'll try to write better if we need to. But I'm going to let f be a function from I to R. Okay, so the interval I is the domain, and it's a function from I to R, and I'm going to pick a point C that is in the interval I. So that's just somewhere in the domain. And then we're going to define the derivative of f at C. Okay, so the derivative of f at C is, well, the notation for it, as I know you are aware, is just with this prime symbol. So it's going to be written f prime of C. And it's going to be expressed as a limit. So it will be the limit as x approaches C. So I'll put it with an x with an arrow to C of, and here it is, you guys have surely seen this, f of x minus f of C divided by x minus C. So let's get that kind of in a box here. This is the definition of the derivative, which I'm sure that you would have seen this in calculus. Now, I do need to add a couple of comments about this. Since we're defining the derivative to be a limit, one of our first concerns is going to be, well, does that limit exist? So I'm going to say here, provided, so we have a little proviso here, guys, provided this limit exists, and it needs to exist in R sharp. Okay, so I'll just remind you from earlier in the book, the R sharp is just the real number line, but with plus and minus infinity included. So it is possible to talk about the derivative of the function being equal to plus infinity or minus infinity. However, we're not going to say that f is differentiable at C unless this limit is a real number. In other words, it should not be plus or minus infinity. So let's add that here. So we say, we'll add a little bit more to our definition. We say f is differentiable at C. F is differentiable at C provided that f prime of C is actually a real number. So in other words, that it's not plus or minus infinity. It needs to be an actual real number. Okay, so that's that. And then if we take any domain, I'm going to add a little bit more to the definition here, guys. It's kind of a long definition. But if D is any subset of I, right, then what we're going to do is we're going to say f is differentiable on D. So instead of just focusing on a specific point C, we can say that f is differentiable on D if f is differentiable at each point C in D, in that domain. So it should be differentiable at every single point of the domain. Okay? So that's what differentiable means. If you're looking for some intuition, guys, if you're looking for some intuition about what differentiable really means, it just means the function does not have sharp corners. So I know you've all seen graphs that have like sharp points on them. Those sharp points are going to be places where this limit doesn't exist. So a differentiable function, you'll often hear mathematicians say that such a function is smooth. meaning it doesn't jerk around. It doesn't have sharp corners. It smoothly flows from one place to the next. So that's kind of intuitively what it means. Is everybody with me so far? Okay, great. So far, so good. Now, this may not be the only way that you've seen the derivative expressed. And I want to show you an alternative, which I imagine will be equally familiar to you from your earlier calculus classes. So here is another note, I guess I'll call it. By the way, I hope you guys are still doing your flashcards. You've got a few more things for your flashcards already. Some definition, and you learned on the last exam, right? That knowing your definitions and knowing your theorems was going to get you some easy points on the test. So keep up the good work with that. Definitely want to have those definitions down. But the note is that by setting H to be equal to X minus C. We can do a little change of variables here. And what we can do is think of F prime of C. All right, well, I've got the definition up here in the box on the top of this board. But if I imagine letting X minus C be equal to H, then you might be able to recognize that having X approach C is the same thing as having H approach 0, right? So H would be approaching 0. And then if I look at the numerator of my fraction, we can think of the f of x as being f of C plus H minus f of C, and then this would be all over H. So let's put that in a box as well, because that is the equivalent definition of the derivative. Does this look familiar as well from your earlier calculus courses? Tell you what, give me a little thumb. Yeah, there we go. Thumbs up if you've seen it before. So both of these boxes should be kind of familiar. They are absolutely equivalent. I don't have to really prove that one of them is better than the other. They are literally mathematically equivalent to each other. So we can use either one. And by the way, I really appreciate all that feedback out there. So thank you guys for that. Super, super helpful. Okay, yeah, so this is an alternative definition. So I'm going to maybe try and do an example now. And this is an example. You could have seen something like this in your calculus course. Oh, this is erasing so easy. Do you know why? It's because I have, well, you can't see that. I have a heater. I have learned through experience that if you have a warm room temperature whiteboard, it will erase really well. I know this because I taught during COVID out in the garage of my house in Colorado in the middle of a blizzard, and I could not erase anything. It was 10 degrees outside, and it was so cold. And I was like, why can't I teach my class out here? And I figured it out. It's like that you need the board to be warm to erase it. All these wonderful things we figure out, right? Through life experience. Anyway, yeah, so let's do an example. First example here, let's let f of x be equal to x to the 4th. So we'll make a specific example. And then as always, I'm just going to imagine C is any real number. So for this function, my interval I can be the entire real number line from minus infinity to infinity. Let's try to calculate the derivative of this. You might have even done something like this in your earlier calculus courses, but I'm just going to start off with one of these kind of examples today, just because it's a little bit easy, kind of an easy warm-up to do. Now, when I'm calculating the derivative, I can use either one of these boxes. They're both equivalent, right? I can use this definition or this definition. And which one you use, it really only comes down to a difference of what the algebra is going to look like. So in some cases, the algebra might be a little bit smoother and easier using this definition. In other cases, maybe this one works better. And that just takes some experience and some time to kind of get comfortable with what situations maybe would it be better to use this definition versus this one. Now, see, for this function, for x to the fourth, I have a choice. If I use the definition on the top, I'll have to factor x to the fourth minus c to the fourth, okay? If I use the one on the bottom, I'll have to expand c plus h to the fourth power. And it's like, which one is worse? Like, I don't know, right? It's almost a personal opinion as to which formulation you prefer. I think for this one, I'm going to use the modified formulation here on the bottom. So I'm going to write this as the limit as h goes to 0 of the quantity c plus h to the fourth minus c to the fourth all over h. Okay, so I'm using the definition in the box here on the bottom for this particular one. Again, the algebra that we have to do here is to just expand out this fourth power of c plus h. So I'm going to go ahead and do that. I'll go ahead and try and write this out. This is going to give me c to the fourth plus 4c cubed h plus 6c squared h squared plus 4c h cubed plus h to the fourth, and then I have to subtract the c to the fourth again from the top. So the numerator gets expanded out and it gets a little bit messy, but it's really not that bad. Okay? And the next step is also just going to be an algebra step. I might notice that the c to the fourth can be canceled. So I can cancel the c to the fourth here with the c to the fourth here. All of the other terms in the numerator have common factors of h. So I can pull out this h, and when I factor out the h from that, I get 4c cubed plus 6c squared h plus 4c h squared plus h cubed. And this is still all divided by h. Okay. So that's just algebra, right? Pretty easy algebra. The next thing to remember is that when we're taking the limit as h approaches 0, right? When the limit is being taken as h approaches 0, h is actually not going to ever be equal to 0 here. And if it's not equal to 0, guys, I can cancel it from the numerator and the denominator. So you can do that because h does not equal 0 at that particular moment because we're taking this as a limit. And so you just end up with the limit of what's in the bracket in the numerator, the bracketed part of the numerator. And for that, you can just view it as a polynomial in h. C is a fixed value, right? It's just some number. We don't know what it is, but it's fixed. So if I just go in here and just plug in 0 for h, then it's going to just look like this, right? You're just putting 0 everywhere that you had an h before. So 4c cubed plus 6c squared times 0 plus 4c times 0 squared plus 0 cubed. That, of course, is because polynomials are continuous. And we have the huge remark that says that if you want to take the limit of a continuous function as x approaches c, all you have to do is plug in c, right? It just equals f of c. So we're using that, right? Let me just scribble here for a moment. Remember this? For a continuous function, the limit of f of x as x approaches c should just be f of c. We already know that polynomials are continuous. Great. So we can use this. And so if I'm evaluating the limits of each of these pieces, all I got to do is plug in 0 for h. It's a plug-in exercise. And so we're just going to be left with the first term there, 4c cubed. And that's exactly what we would have expected. I know you guys all know the power rule. So using the power rule for derivatives, this is exactly what you would have expected. And this is easy to generalize to any positive integer powers of x. It's also easy to imagine doing it for non-integer values of x. Let me give you another example really quickly. if we were to let f of x equal the square root of x, right? And again, we would take c. This time I'm going to choose c to be positive. So I'm just doing another example here, guys, just to show you a slightly, similar but different example at the same time. What if we wanted to take the derivative of this? So we can do that again, but only for positive values of c this time. So what's f prime of c? Well, this time, guys, I'm actually going to use the original formulation. It's totally up to you which one you want to use. I just don't feel like dealing with the square root of the quantity c plus h. Square roots and plus signs don't behave well. So it's actually going to be a little easier, I think, in this case, if we use the original formulation, square root of x minus square root of c all over x minus c. So I'm just simply plugging in for f of x equals the square root of x. I'm just plugging that in to this expression. Looking at that, does anybody have any suggestions for what I might be able to do? And you can use your microphone or you can use the chat. But any suggestions of what the algebra would be here that we would want to use? I know it looks a little funny, but the x minus c that's on the bottom, could we actually kind of artificially factor that? We could treat it as a difference of squares. It's the square root of x squared minus the square root of c squared, right? And so that's actually the way you want to do this. So you just leave the numerator the same. The numerator is still just radical x minus radical c. But then in the denominator, I can factor x minus c as radical x minus radical c times the quantity radical x plus radical c. You can literally just factor it like so. Okay, everybody reading this okay? Yeah, clear enough? And remember that x is not going to be equal to c, which means that square root of x minus square root of c won't be 0. You can cancel the radical x minus radical c, just like before. Okay, and then again, this function 1 over the square root of x plus square root of c, that's going to be continuous as long as the denominator is not 0 and as long as you're plugging in positive numbers. So we can go ahead and just plug in c everywhere we see an x. And so I'm running out of room here, but I'm just squeezing it in. Hopefully it's legible. This is just 1 over radical c plus radical c, which is 1 over 2 radical c. Okay. I think that should be good. And that's exactly what the power rule would have given you as well. If you think of this as x to the 1/2 power and you use the power rule, the derivative is just going to turn out to be that. Okay, so I should maybe add one more line to this solution. Let me come back over here and do that. So in this example, guys, I was fixing some positive number c. But as you can see, this argument works for any positive number c. And so thus we can actually sort of draw the conclusion that the derivative of x, so if we take f prime of x, right, the derivative evaluated at x, it's just 1 over the square root of x for all x greater than 0. That would just be for all x greater than 0. Okay. Give myself a little more space here. So far making sense? Questions? I should have done that here too, right? I mean, basically, f prime of x here, on this first example, it would have been equal to 4x cubed for all x in R, right? We could extend that to any value of c. in the real numbers, and so that's just a general formula for the derivative of f of x. Okay. Well, as it turns out, guys, I mentioned this earlier, we can't really talk about a derivative of a function unless it's continuous. And so that is our first big theorem. Differentiable functions have to be continuous. And I'm going to state that as a theorem. We've done a couple of examples of the definition. Now I want to state the first, I guess, theoretical result. This is theorem 5.1. And this is one that has a pretty short, easy proof. I'm gonna look forward to running this by you and sort of see what you think. So what it says, guys, is very simple. If f is differentiable at c, then f is continuous at c. Okay, so if it's differentiable, then it has to be continuous. We can also think of it in contrapositive form. If a function is not continuous somewhere, well, then it can't be differentiable there either, right? So that's an important thing to keep in mind as well. So I'm going to do the proof of this. Maybe I can prove it right here. Is everybody able to read this okay still? Yeah, okay, good. So let's try to prove that let's assume f is differentiable at c. So c is just some point, right, that is in the domain of the function. So let's assume that f is differentiable at c. I'm going to show that it's continuous at c by using the huge remark, right? So that huge remark from before spring break. So we need to show, I'm going to state what we're going to show here, guys. We need to show that if we take the limit of f of x as x approaches c, we need to show that that limit is equal to f of c. This is the huge remark. The huge remark is a characterization of continuous functions at a point c. So this is what we're going to try to do. Okay, so let's do that. And how am I going to do that? Okay, so to do this, I'm actually, the way I'm going to do this, guys, I'm actually going to subtract. I'm going to rephrase this as the left side minus the right side equals to 0. And I'm going to try to show that that's actually true. So here is how we're going to do this. Okay, this is a little bit of a weird proof. It's not the way the book chose to write it, but I'm going to write it this way, which is I'm going to start with 0 on the left side of my equal sign. And I'm going to replace 0 with f prime of c times 0. Now, I should be very clear here that in order to write that down, okay, everybody could look at this and say, oh, that's obvious, right? 0 times anything is equal to 0, but I want to be careful. Why am I able to write that? I'm able to write that, guys, because f is differentiable at c. Guys, if f prime of c was equal to infinity, then this would no longer be a very obvious statement, right? I need to know that this is a real number. So if it's in your notes, this is where it helps when we have a bigger whiteboard. In your notes, right before we did these two examples, I gave you the definition of differentiable, which was that f prime of c is a real number. So it's not plus infinity, it's not minus infinity, but it does exist and it's a real number. Well, guys, if you take a real number times 0, of course you get 0. No problem with that. Okay, so far, no complaints, right? I should just say this is, maybe we'll just add this. This will help you later to remember why this is true. F prime of c is in R. It's actually in the real numbers. It's not equal to infinity or minus infinity. It's actually in R. That's a little hard to see, isn't it? There's a little bit of a glare on my board here. This just says since f prime of c is an element of R. Okay, so if you can't quite read that, that just says element of R right there. Okay, but now what I'm going to do is I'm going to do another step. F prime of c, we have a formula for that, right? It's the limit as x approaches c of f of x minus f of c all over x minus c. So that's the first term. And then this second term, which is 0, I'm going to rewrite that also as a limit as x approaches c of the quantity x minus c. Okay, so let's just take a look at this really quick. Is that all okay? So this is just f prime of c right here, which is the first term on the left, or on the right. And then I have a 0 here, and I think we would all agree that the limit of x minus c as x approaches c is equal to 0. So guys, both of these limits do exist. They both do exist, yeah? They both exist. And whenever they both exist individually, we have this result. Remember that we can, what is it, the limit theorems? Limits respect addition, subtraction, multiplication, division. So in this case, I have a multiplication, and because both of the individual limits exist, I can multiply them together. I can multiply them together. So I'm going to do that. I'm going to write this as f of x minus f of c all over x minus c times x minus c. Right. Normally, we can't just bust these two factors apart, but we can if we know that each of the individual limits exists. And we do know that each of these individual limits exists. F prime of c exists, and the limit of x minus c is, of course, just 0. All right, well, now I can do my canceling. So this is the limit as x approaches c of f of x minus f of c. All right, and what is that? I'm just canceling the x minus c essentially. And what is this? Well, limits respect subtraction as well. This is just the limit as x approaches c of f of x minus the limit as x approaches c of f of c. F of c is just a constant. So I can split that up. The limit of a constant is just itself. And the limit of the first term is just the limit of f of x as x approaches c, whatever that is. All right. But one last step here, guys. This is equal to the limit as x approaches c of f of x minus the limit of a constant is just equal to that constant. So, sorry, this is a little hard to read here. This is a c. This is limit. So it's the limit of f of x as x approaches c minus the limit of this constant function is just that constant value again. And remember, guys, that all of this is equal to 0. You with me? This is equal to 0, which means that the two things that you were subtracting from each other are equal, right? So that means, let's just wrap this up then. That just means, thus, the limit of f of x as x approaches c is equal to f of c, right? Because the difference is equal to 0. So this is what we needed to show, and now we've got it. Okay. Nice. So differentiable functions have to be continuous at whatever value of c you're looking at. All right, let me get this erased. Oh, this is so nice. So far, so good. I'm not seeing anything in the chat yet. I'm hoping that means everybody's okay. Yeah, okay, great. Make sure you understand every single step, right? This is a proof I might ask you to reproduce. This is on the level of something I'd put on a midterm. It's like, okay, basically I got to prove the huge remark. And the way I do that is a bunch of steps, 4 or 5 steps here that are pretty much exactly what you would expect to do. They follow naturally from each other. So in terms of results that you ought to make sure you know how to prove, I put that one in that list. And when we get around to the third midterm, you're going to see it on the review packet and everything. I mean, it's a really important result that you don't really talk about in your freshman calculus class because you just assume everything's differentiable and therefore continuous. And this theorem kind of gets swept under the rug. But in a class like this is a big result. This is a big deal. Okay, great. So we've got that result. I, of course, would like to comment that the converse of this is not true, and let's see if we can do a counterexample. So just as a quick little remark, the remark would be that the converse of theorem 5.1 fails. So the converse is not true, and well, does anybody think they have an example, maybe a counterexample? Can you think of a function that is, okay, so we're looking for a function that is continuous at a point, but not differentiable. So that means I can draw the graph without picking up my pencil, but that there are sharp corners to it. Because sharp corners, remember, sharp corners basically means not differentiable. Does anybody think they might know a function that's like that? That you can graph it without picking up your pencil, but it does have a sharp corner somewhere. If you do, why don't you put it in the chat? I'll take an answer from anybody. And my internet is slow, so sometimes I have to wait a second. If my parents want me to keep helping them out, I'm going to start. Well, first of all, I'm going to run up their heating bill with this heater. And then I'm going to tell them, you guys got to get good internet so I can check these things. Okay, I see a couple things in the chat now. The absolute value of X is exactly what I had in mind. So Hungju and Ayushi, thank you for that. That's exactly what I would recommend. So let's do that. The example, f of X equals absolute value of X, right? Then F is continuous. Actually, it's continuous on the entire real number line, right? And if we need a reference for that, you guys actually did that in the homework. So this was section 4.1, problem number 1. This was a couple of homework assignments ago. I had you prove this. So the absolute value function is definitely continuous anywhere, any real number. But I claim that it is not differentiable at 0. So however, F is not differentiable at 0. And in order to convince you of that, I have to prove that this limit definition doesn't exist, right? So if I look at f of x minus f of 0 divided by x minus 0. So I'm using the definite, that sort of, by the way, this is usually referred to as the difference quotient. When you're studying this in basic calculus, they'll talk about the difference quotient here. Well, so if I take the limit of that, so if I take the limit as x approaches 0 of f of x minus f of 0 divided by x minus 0, this is going to be just the limit of absolute value of x over x. And so that will be equal to the limit as x approaches 0 of, well, I'll just say 1 if x is greater than 0 and minus 1 if x is less than 0. So this is the derivative. We're not talking here about the original function. We're talking about the derivative. So if x is negative, right, then we have a minus sign that gets absorbed on the numerator. For negative values of x, we'll pick up a minus sign and then cancel the x's. For positive values of x, this literally is just the same thing on the top and on the bottom. And I'm just going to say which does not exist. That limit does not exist. Again, how do we prove that limits don't exist? Well, we usually use sequences. I bet I can come up with two different sequences that converge to 0, but for which I bet I can make two different sequences that converge to 0 such that in this function, which is defined right here, we get two different answers, right? So this does not exist. I'll just add that here so you have it in your notes. This is going back to stuff from before this chapter, but just what you would do here is you would consider sequences. If you wanted to really disprove that this limit exists, you could consider sequences. One of the sequences might be xn equals 1 over n. Okay, that certainly converges to 0. But then I could make another sequence which might be negative 1 over n, which is also converging to 0, and I'll call that y sub n. Okay, but for the xn sequence, all of the f of xn's are equal to 1. And for the yn sequences, all of the f of yn values are equal to negative 1. So the limits of these output sequences don't agree. They don't agree. And again, for this limit to exist, one of our theorems from chapter 3 actually is that for a limit to exist, every sequence that's converging to C has to have an output sequence that's converging to whatever the limit is supposed to be equal to. And that limit would need to be unique, which it's not. So there you see, that's really the easiest way to disprove that that limit exists. So this function is not differentiable at 0, even though it was continuous everywhere. All right. Let me get this wiped off a little bit, and we're going to do another theorem that I think will be very familiar to you.
Can I ask a question?
Yes, please go right ahead.
So for this theorem, for 5.1,
Yeah.
is it used typically to like disprove something is continuous or something like that, or?
No, we would use it to you could use it to disprove that a function is differentiable. So if you knew that your function was not continuous, then you would know that it would be not differentiable. So that's the contrapositive of the statement. Does that make sense, Danny?
Yeah, that makes sense.
Okay, good question. Yeah, that's sort of the spirit of it. I would say overall, this is not a theorem that has a lot of application. This is really more on the conceptual side. Just what is the relationship between continuity and differentiability, right? That's really what this is about. Like how are they related to each other? So hopefully that theorem gives us some insight on that. Okay, well, the next result, I'm still continuing just kind of with the book's flow of things in the first part of chapter 5. This is actually proposition 5.1. So we had theorem 5.1. I mean, I'm really sorry. I don't know if I like the numbering that the book uses. We have theorem 5.1. We have proposition 5.1. Again, you're never going to be held accountable for what the name of the result was with the book's numbering. But this is the sort of the theorem about how derivatives play with addition, subtraction, multiplication, and division. So you guys know these rules already. We're just writing down things that should be familiar to you. I'm going to take two functions, f and g, that are both defined on an interval I. And I'm going to assume that these are differentiable at C. So let's assume that these are differentiable at C. And then I'm going to grab another scalar here. You'll see where this comes in a minute. I'm going to call this A. So let A be another real number. So the A and the C have nothing to do with each other. So I have a real number C and I have another real number A. They don't have anything to do with each other. But then what we're going to say, guys, is that F plus or minus G, make sure that that plus or minus is really clear. F plus or minus G along with F times G along with A times F and along with F over G. And on the F over G one, I need to add a little comment here. This is going to be provided that G prime of C is not 0. I'm hoping that's all legible. So this says F plus or minus G. This is F times G. This is A times F. And this is F over G, provided that the derivative of G at C is not 0. These functions are all differentiable at C. So those functions are all differentiable at C, and where the real guts of the theorem is the formulas for these derivatives. So there's 4 parts here, guys, 4 things we need to write down. First of all, if we take F plus or minus G, then we want to take the derivative of it at C. So we're putting the plus and minus together because they work exactly the same way. This is just going to be F prime of C plus or minus G prime of C. Okay, so derivatives just totally respect addition. The second one is that if I want to take the derivative of F times G and evaluate it at C, so the derivative of F times G evaluated at C, you guys all know this one. This is the famous product rule, right? So this is going to be F of C times G prime of C plus F prime of C times G of C. So this is, the first term, the first function times the derivative of the second plus the derivative of the first one times the second one. So that's just your good old product rule. And then the third one is where you have A times F. And you want to take the derivative of that at C. In this case, the A is just a scalar. So I'll remind you from calculus, you guys all know this, that scalars can just be factored out, right? So this is just A times F prime of C. We can actually just view that as a special case of number 2, right? It's a special case of number 2 because after all, if one of your functions was a constant function, it would have a derivative of 0. And so in your product rule, I guess it would be this first term here would just be gone. And you would only have the second part with the constant, with the G function being a constant. So number 3, we don't have to prove it. It's just a special case of number 2. And then lastly, the fourth part, what about the derivative of F over G? So if we take the quotient F over G, then I'm sure you guys remember that there's a rule for that as well. It's called the quotient rule. And how does that work? Well, it's low D high, okay? So that would be G of C, F prime of C, minus high D low, which is F of C, G prime of C, all divided by the denominator, which is G of C, quantity squared, so low squared. So that is your good old derivative rules for addition, subtraction, multiplication, and division. Absolutely true. Okay, so in terms of the proof of this, and let me just say a couple words. As soon as I'm done with the proof of this, we'll take a 10-minute break. I am going to do that here shortly. But let me just make a couple of comments here about the proof. First of all, for part 4, I'm going to do that with you guys next week in class as a group work. So part 4, we're going to do this, I'll just say here, C group work number 11. So that is one of the exercises in the next group work, but I don't really like doing group work over Zoom. So we'll save that till I come back next Tuesday. We'll do a group work and I'll let you guys do that one. So that's number 4. 2 is, as I mentioned, a special case of 3. So that means I don't have to do 2. Or sorry, that means I don't have to do, I'm sorry, I wrote that backwards. I wrote that backwards. 3 is a special case of 2. I got those reversed. I'm so sorry. 3 is a special case of 2, so I don't have to prove 2 either. I really just have to prove 1 and 2. And actually for number 1, I can focus on the plus sign, because if you have F minus G, you can imagine that as being F plus -1 times G. Okay, and -1 times G is just something that number 3 can handle. So for the proof of number 1, right, the way we would do this is we would, I guess I'll write it down here for you. We would take the limit as x approaches C. I'm going back to the definition of the derivative, right? So it would be the limit as x approaches C of F plus G of x minus F plus G of C all over x minus C. All right, so it'll be something like that. And we just need to figure out what this is equal to. And we know that F plus G of x, well, that's just, so I'm gonna go ahead and clean this up right away. The denominator is x minus C, no worries there. In the numerator, what I have though is I have F of x plus G of x minus F of C minus G of C. So we can write that as a extended numerator as such. Get this erased a little bit more. Okay. And I bet you know what I'm gonna do now. I'm just gonna regroup the terms in the numerator, right? I'm gonna rewrite this as the limit as x approaches C of F of x minus F of C all over x minus C. We'll just put this all into some brackets here. Plus G of x minus G of C all over x minus C. So put all the F stuff in the front, put all the G stuff in the back, and we can split this apart into two separate limits as long as both limits exist, which they do, right? Which they do. So this is the limit of F of x minus F of C over x minus C, plus the limit as x approaches C of G of x minus G of C, again, all over x minus C. Again, why is this step legit? It's because of our limit theorems, which says that you can do this as long as the individual limits do already exist. And they do, because we assumed at the beginning, guys, that F and G are both differentiable to begin with. So both of these limits already exist. So splitting this up is totally okay. And so we just get F prime of C plus G prime of C. That's totally okay. So limits respect addition. Limits definitely respect addition. Okay, one more. Let me do the product rule real quick, and then we'll take a break. Okay, does that sound fair? All right, let's do that. Hearing no objections. If you want to object, you got to speak up. Okay, so I'm going to do the product rule here. So for this one, number 2, we're going to take the limit as x approaches C of F times G of x minus F times G of C all over x minus C. So I'm just using the definition of the derivative again, but applying it to F times G. And this is one where we're gonna do a little trick. So give yourself enough room here, guys, to write out this little trick that we're gonna use. This is the key step here. The first part is just f of x times g of x. That's what it means when it says f times g of x. That's just f of x times g of x. And what I'm gonna do, guys, is I am going to insert into the middle of this, I'm gonna do minus f of c g of x, and then plus f of c g of x. And then I'll subtract f of c g of c. So just like so. So I've expanded the numerator, but what I've done is in the middle, I have just added and subtracted the same thing. F of c g of x, okay? So it's a little trick to get this to work. And now I'm going to split this thing apart. So this is the limit as x approaches c of, so for the first part, I'm going to write it as the quantity f of x minus f of c times g of x all over x minus c. And then plus the second part is the limit as x approaches c of the quantity of f of c times the quantity g of x minus g of c all over x minus c. Just like that. As always, guys, just slow me down if there's any question here. So I basically took the first two terms and put those on the left, and I took the last two terms and put them on the right, and I made those into two separate limits. It's just a nice little trick. And what you can now do is you can view this as, well, this is actually a product here, guys. This is actually a product. The first limit is really just the limit as x approaches c of f of x minus f of c all over x minus c times the limit as x approaches c of g of x. And the second term is very similar. It's just the limit as x approaches c of f of c. And I'm running out of room, no surprise. Limit as x approaches c of g of x minus g of c all over x minus c. That's going to be kind of tough to read. Let me try one more time. I have to have really like a surgeon's fingers here to squeeze this in here. So this is the limit of f of c times, I think you know what I'm writing here. This is the limit as x approaches c of the fraction g of x minus g of c all over x minus c. I hope that's sort of legible. I'm gonna bring this in really close there. Right, so that's what we're looking at. I know there's a little bit of a glare there too, but you're just breaking it up into sort of four separate terms, right? So the first term, the second term, the third term, and the fourth term. This first one is just f prime of c. And what is the limit of g of x as x approaches c? What's that going to be equal to? Anybody? What's this equal to, guys? Somebody help me.
G to C, G of C.
Yeah, it's g of c. And again, what's the reason? The reason is g was differentiable, which means it's also continuous. And if it's continuous, then we can use the huge remark that says that this limit would just be g of c. Exactly. Okay, on the second term, the limit of f of c is just f of c because that's a constant. And then the last part is the g prime of c. So I think that's basically what we were supposed to end up with. The terms are in a different order than the way I stated them in the theorem on the other board over there, but it's more or less the same result. Okay, so guys, as of now, you can use the product rule in this class. Gee, it's a real analysis course that we have taken 10 weeks to be able to even use the product rule for. I think that's kind of funny, but we are definitely there. We're definitely there. Okay, well, guys, we're going to take a 10-minute break. There is one rule over here that's missing. What am I missing? I've got the product rule. I've got the quotient rule. I know how it respects addition and subtraction. Is there something missing in terms of derivative rules?
Composition.
Composition. Ayushi's got it. Yes. And what rule? Does anybody remember the name of that rule that helps us to take derivatives of compositions? I'm sure you know it.
Chain rule.
The chain rule. It's been spring break, but it hasn't been that long of a break, right? We all remember that, the chain rule. So after we take a 10-minute break, let's come back at about 2:20 or so, and I will do the chain rule for you. That one turns out to be a little tricky. You're going to see the proof is a little tricky. So we'll take 10 minutes here, and then we'll come back and prove the chain rule. So I'll see you in just a few minutes. Well, guys, if you're out there within the sound of my voice, I'm going to start again in just about a minute or so. So this is a good time to find your way back over here. And as I said, we'll start in about 1 more minute. Thank you again for being here, guys. Really appreciate you putting up with Zoom here today. Nice. Anybody get to do anything fun for spring break? We're just gonna same old, same old.
Same old, same old.
Okay. That's not always a bad thing. Well, it's hard to believe we only have about a month to go. So the spring break is sort of 2/3 of the way through the semester, and that means we don't have to work for quite as long on this next stretch as we did leading up to this point. But I know that everybody was ready for that break, I'm pretty sure. All right, well, I think I'm gonna go ahead and get started. It's been about 10 minutes since we took a little break here. I promised you I was gonna do this chain rule theorem, actually, but before I do that, I thought of another example I thought I might show you, which is this example over on the other side. Now I'll use this maybe in an example of the chain rule as well, which is, and I'm sure you've probably seen this before, and I know you already know the answer. What is the derivative of the sine of x? Right, that's a good example of this. So let's just practice that. I'm going to go over to my other board here so I can talk about the sine of x. Now this is going to rely on a little bit of trig. So with this example, keep in mind we are going to kind of utilize some things that we would have learned in a trig class. But again, the idea of finding the derivative of the sine of x would be to use the definition, right? So it's just going to be a limit as x approaches c of the sine of x minus the sine of c all over x minus c. So that's just coming from the definition. And actually, you know what I think I would prefer to do is, I think this is one of those examples, guys, where I want to use the alternative definition. I'm so sorry, I'm gonna change this. I wanna use the alternative formulation just because the algebra is a little nicer. So you might remember that one from earlier today as well. This is the limit as h approaches 0 of the fraction sine of c plus h minus the sine of c all over h. So I think I'm going to use this version here. So this is f of c plus h minus f of c all divided by h. The reason that I want to use this formulation is that there is a trig identity that will allow us to evaluate the sine of c plus h. So I'm going to try and use that trig identity here. So let's see if we can do it. What it is, so this equal sign right here is going to be based off of trig. So it's still the limit as h goes to 0. And we still have an h on the bottom of this fraction. But there's a formula for the sine of c plus h, which you may or may not have ever memorized it, but I'll just write it down for you here. It's the sine of c times the cosine of h plus the cosine of c times the sine of h, and then we still have minus sine of c over here on the end of it. So it's gonna look something like that. Bring this in a little closer here, make sure everybody can see that okay. So we're subtracting the sign of C on the end of it here. And the trick to doing this from here is there's two terms in the numerator that both have the sign of C in them. And I'm going to try to factor a little bit. So this is going to be the limit as h goes to 0 of, and then I'm going to write this as sine of C times the quantity cosine of h minus 1. And I put that all over h. And then the term that's missing, I guess I'll just add this over here on the right. So I'm putting some brackets in here to kind of split this up. And then on the right, what we have is cosine of C times sine of h over h. Okay. So is that readable? Yeah, so that's just sort of regrouping everything. And now I'm going to use my limit properties to split this up. Obviously, I have the sine of C, which I can pull out in front of the first term, times the limit as h goes to 0 of cosine of h minus 1 all over h, and then plus the cosine of C times the limit as h goes to 0 of the sine of h over h. Oh, that's a pretty bad glare right there. Let me write this a little bit lower so it doesn't get in the way of that glare. So this is going to be plus the cosine of C, right, times the limit as h goes to 0 of the sine of h over h. Is that more readable? I think so. Yeah, okay, good. So that's what we would have there. Now, here's where we have to use a little bit more trig. This first limit right here, the limit of the the limit of the cosine of h minus 1 all over h as h approaches 0 is actually equal to 0. And similarly, the limit of the sine of h over h is actually equal to 1. So you can prove those limits using power series expansions of sine and cosine if you would like. That's often the way that it's done. But we're going to take those as given values. These are pretty famous, actually. It's pretty famous that the sine of h over h approaches 1 as h goes to 0. And cosine of h minus 1 over h goes to 0 as h goes to 0. If you're willing to believe all of those results, you can see immediately that the answer is just cosine of C. And this is, of course, what you would have expected, right? The derivative of the sine of C is the cosine of C. So let's write that down. F prime of x is equal to cosine of x. This is for all x in the real numbers. So for every real number x, the derivative of sine is cosine. And by the way, you're welcome to use any of these facts that we're proving today anytime going forward. I'm sure you also know that the derivative of the cosine is the negative of the sine. If you wanted to, you could take that as an exercise. Just try it on your own and see if it makes sense to you. Questions on this one? So this one does rely on a couple of things from sort of outside of this class, right? The trig identity that we used near the beginning, as well as these two limits that are, as I said, very famous results. That you probably saw in your freshman calculus course. Not going to go over them. By the way, you could prove those limits. If somebody did challenge you to prove these two limits that I've put here, the easiest way to prove what they are is to use L'Hopital's rule. Of course, L'Hopital's rule uses derivatives. And so we don't want to get into a catch-22 with this, but we are going to do L'Hopital's rule, probably next week. So it's coming up very soon. And once we have L'Hopital's rule, we could prove limits like that. So anyway, that's getting a little ahead of ourselves. I've still got to prove this chain rule over here. And that's the next thing I'm going to do. Unless there's any kind of a question. I'm not seeing anything in the chat so far, so I'm gonna assume you guys are good. Man, time flies. I don't know what it is, but we only have 20 minutes left. Okay, let's state and prove the chain rule now. This one's a little tricky. So let's write it down carefully. Theorem 5.2, which is the chain rule. I actually am going to create two different intervals, I and j. These are intervals. So let's let I and j, which are subsets of R, let's let those be intervals. Those are both intervals. Okay, and I'm going to assume that f is a function going from I to j somehow. Oh, I need to back this up a little bit. So sorry. Make sure that's all visible to you there. So I'm going to assume that f goes from I to j, and that g goes from j to r. It's obviously important if I'm going to compose functions together that the outputs of the first function need to belong in the domain of the second function. So that's why the codomain of f is j in this theorem, and that becomes exactly the domain of g. So the outputs of f are going to become the inputs into g, and that's the setup of that. Then I've got to grab my my point c again. So c is just going to be an element of I. So we take our point in I right here, and I'm going to assume that f is differentiable at c, and g is differentiable at f of c. So just remember what that means again. That means that the limit of the difference quotients exists at c and exists as a real number. So if you need to, you've got it in your notes from the start of class today. Make sure you know what do I mean when I say f is differentiable at c? What does that mean? And g being differentiable at f of c, what does that mean, right? So we have to make sure we still remember those definitions. But then the conclusion is that if we look at the composition of g with f, so g composed with f, now this would be a function from I to R, right? The conclusion is that this composition function, g composed with f, is differentiable at c, and we can even give the formula for the derivative, and this is the formula that I'm sure you guys are familiar with. The derivative of the composition of g with f is calculated using this, this is the chain rule, right? G prime of f of c times f prime of c. So that's the chain rule. That's our good old famous chain rule for taking a derivative of a composition. Okay, so let me give myself a little room here. Now, that statement isn't surprising. Of course, we all know it. It turns out the proof of this theorem is not quite as straightforward as maybe those other derivative rules. The product rule, the chain rule, the product rule, the quotient rule, those follow a pretty predictable proof. But there is a very popular wrong proof to this theorem, and I'm going to actually present it to you. You can choose whether you want to write it down or not. Since it's wrong, we're not going to keep it, but I just want to show you what is tempting to do here, but which doesn't actually work. Okay, so I'm going to show you what is tempting to do, but which doesn't work. And here is what the wrong proof would look like. You would take the limit as x approaches c of the quotient. So this would be g composed with f of x minus g composed with f of c all over x minus c, right? That's how you would start. And the way that you would maybe try to break this down is you might think of this as being, so this is going to be where we get into trouble with this. So what I wrote down right now on the first line, that's just the definition of the derivative. So that's just trying to calculate the left side of our chain rule. But the way that this can sometimes get messed up is I'll see people do this. Oh, it's g of f of x minus g of f of c, right, over, and so then what they do, here's the trick. They put the x minus c over here. Again, guys, this is the wrong proof. So why is it wrong? Well, what they do is they put f of x minus f of c right here, and then they put f of x minus f of c right here as well. So you notice that what's in the, what I did is I inserted a denominator right here that is the same as the numerator right here. And the reason for doing that is that what you've got over here looks like f prime of c, right? F of x minus f of c all over x minus c. And this one looks like the derivative of g evaluated at f of c, right? So instead of c, you have f of c in the place where you would have had c normally in the definition. But this does not quite work. And the reason, and this is a little hard to see as well, so we just make sure that this is going to be visible. That looks like f prime of c right there. Yeah, so this does not work, guys. And what's wrong with this proof is a little bit subtle. What's wrong with the proof is a little bit subtle. The thing that's wrong with it is that, okay, guys, as x approaches c, I do know that x will not be equal to c. So this denominator up here, x minus c, that denominator is not going to be 0, for sure. However, even though x does not equal c, f of x might equal f of c. Even as x is approaching c. So that means that x is not equal to c, but f of x might be equal to f of c, which would mean you would have a 0 on the denominator here and a 0 on the numerator there, and you've just created sort of a 0 over 0 inserted into this proof here. So the problem with this, if you want to know why is this proof not valid, why is this a wrong proof? The problem with this is that as x approaches c, right, as x approaches c, we might have f of x equal to f of c. Like that could happen, yeah? That could happen. That would be, and this would mean that you have a dividing by 0 problem. So now you have a dividing by 0 problem. So, so this whole proof is wrong. And it's a popular idea. It seems like it should work, but it does not quite work. So I'm going to come over here now and present what I'll call the correct proof. Are there any questions about that? Does everybody see what I'm talking about? Yeah? Again, I see a few webcams. I appreciate that. Okay, yeah, so that's what's wrong here. So we have to work a little bit harder. We have to work a little bit harder here, guys, and we're actually going to create a new function. So here comes the correct proof now, okay? So here's what we're going to do. We are going to define a new function h, which goes from j to r. So that's exactly the same as how g behaves. G is a function from j to r. In this proof, I'm going to create myself a new function h that goes from j to r. And I'm going to define it as follows. H of y. So y is going to be my input here. I'm going to use a y instead of an x. And that's really because the y is going to be like an output of f. So that the f is going to take x as an input, and it's going to produce y as an output. And that output becomes an input into h. And here is how we're going to define this function. it's going to be done piecewise. It is going to be done piecewise. And the way we're going to do this is we're going to define this to be g of y minus g of f of c all over y minus f of c, as long as y does not equal f of c. Okay, I know there's a little bit of a glare there. I'm gonna try to avoid hitting that spot. I have to figure out how to define this function when y does equal f of c. So I did not write anything in here. I see there's a bit of a glare there. So what is the value here? Well, what we're going to do here, guys, is we're going to define this to be g prime of f of c. So that's how h is going to be defined. Let me come back over here. So we have to be a little careful with this proof. It's a little tricky. So to start off the correct proof, guys, I'm going to make a new function that's not part of the theorem statement. I'm calling it h, and it goes from j to r, and it looks like the derivative of g, basically. But I got to be careful. When y equals f of c, I cannot divide by 0 in this first part of the definition. So as long as y does not equal f of c, I'm okay with this. But when y does equal f of c, I got to do something else, right? I can't divide by 0. So I got to do something else. Now notice, guys, g, what's the assumption? G is differentiable at f of c. That means that this does make sense. There is a derivative, there is a value here for the derivative of g at f of c. And so what I've defined for h here is perfectly reasonable. Okay. So that's my function h. Now, how does that make this proof work? Well, I'm going to note that h is continuous at f of c. And the reason for that is that, well, we could argue that by using the huge remark, right? So if we take the limit as y approaches f of c of h of, h of y, well, so I claim that h is, I'm going to use the huge remark here, that this is just by definition, this is the limit as y approaches f of c of that fraction. Notice that y does not equal f of c right now. So this is just g of y minus g of f of c, all divided by y minus f of c. All right? And by definition, that is g prime of f of c. That's the derivative of g evaluated at f of c. That's exactly what that would mean. And so by the huge, so this becomes h of f of c. Sorry, my check mark should go here. My check mark should go here. So I'm using the huge remark right now to show that h is continuous at f of c. So if I evaluate h at f of c, it's the same as taking the limit of h of y as y approaches f of c. So that proves that h is continuous at f of c. Okay. So now I would like to note that for all y in the interval j, so we take any value y in that interval, g of y minus g of f of c will be equal to h of y times the quantity y minus f of c. So all I did there, guys, if you take a look here, what did I do? I basically took this formula, this fraction, and I moved the denominator to the other side. And so for all values of y that are not equal to f of c, this is just an algebraic rearrangement. And when y does equal f of c, notice that both sides of this equal sign are just 0, right? So if I plug in f of c everywhere I see a y on this equation, I get 0 on the left and 0 on the right. So that equal sign is valid in that case. Okay, so where am I going with all this? Sorry, it's taking me a little bit to get this written down. So this means that for all x in I, if instead of y, if I put in f of x, then this should still be true because all of the f of x values end up being values in j. So I'm just going to replace y with f of x everywhere. And we'll get something that looks like this. I'm just replacing y with f of x. That's for all x in I. And I'm going to take that equation, guys, on both sides of the equal sign, and I'm going to divide through by c. So I'm going to divide through by x minus c. So on both sides of the equal sign here, I'm going to divide through by x minus c. And now I'm going to take the limit as x approaches c on both sides. So this implies that the limit, we're almost done, as x approaches c of g of f of x minus g of f of c all over x minus c is equal to the limit as x approaches c of, I'm going to write this as h of f of x, and then I'm going to make my difference quotient f of x minus f of c all over x minus c. So I'm just literally taking a limit on both sides of this expression. You guys with me so far? This is the correct proof. This is now the correct proof. I hope it's making sense so far. The left side, guys, this left side is just the derivative of g composed with f evaluated at c. That's on the left side. And what do we have on the right side? Well, we have h of f of c. Remember that h is continuous at f of c. So when you take the limit of h of f of x as x approaches c, you just get h of f of c. And then the second part of that limit is just the derivative of f at c. So that's f prime of c. And by the way, what is h of f of c? I'll come back to my function over here, the way I defined it. If I look at what is h of f of c, it's just g prime of f of c. And that's being multiplied by f prime of c. It's a little tricky. It's a little tricky. I don't think I would probably give you this one on the test. I might ask you to do the product rule, or I might ask you to prove that differentiable functions are always continuous. I don't know that I would go as far as a theorem like this, at least not without telling you to be prepared for it, because it's a little tricky. We have to construct this function h and then prove that it's continuous at f of c. And from there, mostly it's an algebraic proof. It's not that bad, but it's a little bit tricky. Does anybody have any questions though on it? At least if this first pass through with it, does it look okay? Just see. Well, I haven't lost anybody so far. I'm happy to see that. I mean, not lost anybody from the Zoom room. Hopefully I haven't lost anybody mathematically either. But at any rate, guys, we've gotten a lot done today. We've learned the definition of the derivative. We've learned how derivatives are related to continuity. And we've proved all of these familiar theorems about derivatives. So we've learned how it respects addition and subtraction, the product rule, the quotient rule. Now we have the chain rule. I'm not going to be spending a lot of time in this class just practicing derivatives. I expect people to know how to put these different rules together, right? You've done that in your calculus classes in the past. Maybe you have to do the chain rule and the product rule in the same function. You might have a function that requires both. Or you have to use the product rule, the quotient rule, and the chain rule, and addition and subtraction all in one go, all in one problem, right? Stuff like that, you should not be expecting your Math 350 instructor to do a ton of practice with that. It's not really the point so much in this class. If I ask you to do one of those, it's sort of a freebie. I'm expecting like, oh, everybody knows these rules and can apply them. So you won't see me coming in here on Thursday doing a lot of examples of the chain rule or the product rule or the quotient rule and whatnot, right? What we're going to do next time, though, is we're going to start focusing on the applications of derivatives. And I mean theoretical applications. We're going to talk about local extrema. We're going to talk about things like the mean value theorem, Rolle's theorem. These are results that may ring a bell from your earlier calculus courses, and they are more on the theoretical side of the ledger. But on Thursday, we're going to have a chance to really practice in more on that and get away from the definition of derivative. So almost the entire class today, we keep going back to the definition of the derivative. On Thursday, we should be doing a lot less of that. And it's going to be more about the applications of it that we can make from here. That's all I've got, though, for today, guys. Is everybody on board? Are there any questions here before we kind of sign off from the session? All right. If not, don't forget, guys, I do have office hours tonight. If you're having any questions on the homework that's due this evening, be sure to come back after 8 o'clock. I'll be glad to talk to you. But thanks for coming into Zoom. I appreciate you being so flexible with me again this week. But we'll be right back here again on Thursday one more time, and I'll look forward to seeing you then. Thanks for today, guys. Take care.
That piecewise function you used for this one, was that something that you showed how you derived, or that's just the given?
It's sort of pulled out of the sky there, John. It's one of those things where it's what makes this proof work. And somebody way more brilliant than me, who came along way before I ever existed, figured out that, aha, this is how we sort of tweak this wrong proof. The idea behind the wrong proof is good. That idea works. What's the problem with it is that little detail I pointed out. So this is the workaround. It's not that we're like completely scrapping the first proof. Instead, what we're doing is we're sort of trying to make that first proof work by doing a tweak to the wrong proof. And this is the tweak, is to introduce this function h. But yeah, it takes a little getting used to it. When I first saw this, I thought, wait a minute, this is way harder than it should need to be. But it actually, I mean, I've done it now enough times that it all makes sense to me. But when you're first seeing this, just know that, like, when I first saw this, I was like, whoa, that seems kind of a little bit far-fetched. Like, where did that come from? But over time, I've come to love it a little bit. And I feel like by showing people what's wrong with the sort of the more obvious proof, that does help build the intuition for how we actually get a proof that will work. Basically, we take what we did in the wrong proof and we just say, well, we're going to use that as long as we're not at f of c, right? And then we just have to define this other point here at f of c, because that's where all the problems occur with the wrong proof. So that's kind of the idea behind it.
Gotcha. And then as we're going through that proof, you would use the f of c as just a constant. Is that because f of c is fixed?
That's right. C is fixed, f of c is fixed, and g of f of c. They're all fixed. And we're assuming up here that the derivatives all exist at all the right places. So f is differentiable at c, G is differentiable at f of c. This is what makes this thing work.
Gotcha. Okay. I will see you at office hours tonight, Professor. Thank you for your time today.
Take care. Thank you for being here.